One of the main goals of a DPU is to offload an entire network stack, including its control plane. Today, we will focus on OVS offload to Marvell's DPU and the exploration that was done with P4-OVS in an IPDK environment. Next, please. So what OVS offload means? It means that all OVS services are running on the DPU cores. In terms of the host, the entire OVS is offloaded to the DPU, but the actual data path flows are either processed by the DPU cores or by the DPU hardware, which is of course the most desired option to gain optimal results. It provides full connectivity between host and DPU containers, which can also be used for service chaining functionality. Next, please. Here we can see OVS offload use case as supported by a Marvell DPU. In a typical use case, the OVS and the containers are both running on the host. As part of the infrastructure offload step, the OVS was offloaded to the DPU ARM cores. In addition, as Marvell's DPU contains powerful ARM cores, containers can also be offloaded. And finally, by offloading the OVS flows to the hardware, we can gain optimal connectivity between all the containers, those on the host as well as those on the DPU. Next, please. Next, we will describe a DPU POC we did using IPDK. The motivation was to explore P4-based solution for the Octeon DPU family. And the IPDK looked like a good candidate to be used for that. The general goal for this POC is to run a DPU use case with P4-OVS in an IPDK environment. Next, please. We started with IPDK running on the Octeon R cores. Basically, we took the IPDK demo as it's running on a host and duplicate it on ARM platform. IPDK demo contains P4-OVS, which runs the P4 application with P4 DPDK target. It exposes virt.io interfaces that in this case attach to virtual machines and forwarding traffic between them. In this step of the POC, we also solved a few ARM integration issues and upstreamed them. Next, please. Once we had the basic IPDK demo running on Octeon, we moved to a DPU mode. In this mode, the virtual machines are running on the host cores and attached to Octeon virtual functions. In Octeon, all embedded interfaces are PCI interfaces, so we had to add a DPDK bridge application to connect the SDP PCI interfaces, which is actually a virtual function representer interface, with the virt.io, which is the only supported interface type in the current IPDK. So after connecting all the dots, we could now forward traffic between the virtual machines using the P4-OVS on the DPU side, and we could also do some performance measurements based on the P4 DPDK target, which is a software-based P4 target. Now we will see a short demo demonstrate that.
So here we have a remote machine that we use in order to test our setups, our hardware. What we can see here on the left-hand top side is the IPDK container running the OVS, the P4-OVS. It was built on the ARM architecture, as was described previously. Here we have another console, SSH console to the. This is direct serial connection to the board, and here we have SSH connection to the same board which we use to invoke the IPDK execute commands, which of course can be executed directly on the container, but we are working according to the README and the IPDK CLI, which allows this execution of commands externally, directly on the container. We can see here the commands as they are described in the README, the exposing of the vhost devices, and finally, on the way, we are invoking the commands for the L3 forward and the pipeline. And here at last, we have the rules for the OVS forwarding, which follows up is the host side. On the host side, what we can see here are two namespaces, each of which has a VF, an exposed VF, as was described earlier. And they are configured such that the static ARP forces the packet and data traffic to go in the direction we want, which is from these namespaces to the VFs and then to the actual hardware and the OVS, which directs them according to the rules that we are describing here from one side to the other. We can see the IP addresses of each of the namespace. And we have a server, an iPerf server running on the side of the .87. Here we have a previous connection that we showed. Now we're going to show it live. So it's listening on 192.168.1.87, and it's really the connection is arriving from the .88, and I'm going to start it right now by simply running the iPerf towards the server. And here we can see the bitrate. And that concludes the demo.
Okay, so now we saw a live demo of the previous DPU use case. And now we want to conclude. So here are a list of findings we want to share. IPDK was working smoothly on Octeon DPU, but just after we added the ARM support. We found that P4 DPDK target has some performance limitation, in particular with CPU scalability, as currently only one core is supported. And as mentioned before, PCI device cannot be added and only VirtIO is supported. And this is very mandatory for Marvell as all our interfaces are PCI type. So thank you.